Hey there, we're going to go over some notes for projectiles that are launched at an angle. And let's kind of draw out what that might look like. So let's say we have a soccer ball right here, and it's kicked, and whenever it's kicked, it kind of goes in the air and does something like this. And so now we have this angle that this soccer ball is launched by. And so if we look at a little snapshot, let's say right here of this soccer ball, and we draw our free body diagram, the only force that we're going to have is Fg. So there are some similarities between the horizontal projectiles and these here that are launched at an angle, and that is that in the y direction, we're basically still going to treat it like a free-fall problem. And so your acceleration in the y direction is still going to just equal g, because the only force here is that gravitational force. And looking in the x direction, we still don't have any forces, just like in the horizontal projectiles. So your velocity in the x direction is still going to be constant. But now, with these projectiles launched at an angle, your initial vertical velocity is not going to be equal to zero, because whenever this was launched, it had a velocity in both the x and y direction. So the horizontal projectiles, your v naught in the y direction was equal to zero, but now we actually have a vertical velocity. So let's kind of draw what that looks like. If I make the velocity vector, and here's my v naught, so the initial velocity that it was kicked by, what we have to do is we have to resolve this vector into the x and y components. So we have a v naught y, and we have a v naught x. And this right here is the angle that it was launched by. And so if we do our trig, what we find is that the initial velocity in the x direction is going to be v naught cosine theta, and the initial velocity in the y direction is going to be v naught sine theta. So we have an extra step here where we have to resolve our initial velocity into the x and y components. So let's kind of draw this soccer ball and draw all of our velocity vectors to kind of see what that looks like as it's moving through the air. So if the soccer ball is right here, and again, it's launched at an angle, so we're going to look there, let's say right here, and let's say this is the max height, and then we'll turn around, it starts falling back down right here, and again, right before it hits the ground. So let's draw those velocity vectors, okay, not force vectors, but velocity vectors. So my Vx would look something like this. And so, like we said a while ago, in the x direction, it's still going to stay constant. So everywhere on here for your velocity vector, you would draw one the same size as that initial Vx. Now let's kind of look at our y direction. So initially, it was launched with a velocity in the y direction, and that is actually going to be my largest velocity vector in the y direction. And what happens is this, vertically speaking, it starts to slow down as it moves up throughout the air. And so this velocity vector should be a little smaller. And at the very top, you're not going to have a vertical velocity vector, because vertically speaking, at the max height, this right here is your max height, your Vy is going to equal 0. So vertically speaking, it kind of comes to rest at that max height, and then it starts to speed up here in this opposite direction. So here's your Vy and Vy. Now your initial vertical velocity, this one right here, when your delta y is equal to 0. So in other words, when it reaches the height that it was launched from, it's going to equal the negative velocity here. So at y, delta y equals 0, your v naught is just going to equal a negative vy. So let's kind of look and see what this looks like in solving a problem. So this one here says a soccer ball is kicked at a 37-degree angle relative to the ground, and we're going to solve for the, and the velocity, the initial velocity is 50 meters per second, and we're going to solve for the maximum height of the soccer ball. That's my delta y. And we're going to solve for the height of the ball after a time of 2 seconds. And then also we're going to solve for how far away it lands. So that's my delta x here. So let's start with part A. And the first step that we need to do in these projectiles launched from an angle is we're going to have to resolve this velocity into its x and y components. So your initial velocity, v naught, is equal to 50 meters per second. But we have to break that up into our v naught y and my v naught x. My angle was 37 degrees. So for my initial velocity in the x direction, it's going to be v naught cosine theta. So that's going to equal 50 meters per second cosine 37. And what you end up with is 39.93, or basically 40 meters per second. And in the y direction, so v naught y, it's going to equal v naught sine theta. So that just ends up being 50 times sine 37 degrees. And you end up with 30 meters per second. So the first step here is we need to break up this velocity into its x and y components. Now we're going to kind of do that same process where we're going to make our table of our x and y components. And so horizontally speaking, we know that our v naught, we said, was equal to 40 meters per second. My initial velocity in the y direction is equal to 30 meters per second. My acceleration in the x direction, it's still equal to 0 because it's still moving at a constant velocity horizontally speaking. My acceleration in the y direction is negative 10 meters per second. And the reason why we say it's negative there is because the initial vertical velocity is going up, and we said that was a positive 30. And looking at that free body diagram, FG is going down, right? So that's going to be a negative 10 meters per second squared. And then at the max height, remember, because that's what we're solving for, what is the maximum height? Your final vertical velocity is going to equal 0 meters per second. And then we're solving for what is the maximum height. That's my delta y. And looking at my chart of my known variables, we already have 3 things here in that y direction. So we don't care about time based off this information. And so now we can pick our kinematic equation, the one that doesn't involve time. And so we have v squared equals v naught squared plus 2a delta y. We have a 0 in here. That's that final velocity. So really I'm left with 0 equals v naught squared plus 2a delta y. Now we're going to manipulate this equation for our delta y to solve for that max height. So I'm going to subtract the v naught y over, so negative v naught squared equals 2a delta y. And then we're going to divide both sides by that 2a to cancel that out. So your delta y is just going to equal negative, and then in parentheses we'll go ahead and substitute that velocity of 30 meters per second, that's squared, divided by 2 times we had negative 10 meters per second squared. So my negatives are going to end up canceling out right there. And your max height then is going to be 45 meters. For part B, we're asked to solve for the height of the ball after 2 seconds. So again, let's go ahead and make ourselves our table. We have x and we have y. Let's fill out our known variables. So we got v naught, x is equal to 40 meters per second. V naught y is equal to 30 meters per second. Acceleration here is equal to 0. Over here it's negative 10 meters per second squared. And then we know that our time is equal to 2 seconds. And what we want to know is how high is it after 2 seconds. So again, we have 1, 2, 3 things over here, and now we can solve for our delta y. And so for this one, we don't care about the final velocity. So we want an equation that doesn't involve the final velocity. So delta y is equal to v naught t plus 1/2 at squared. So there's my equation that doesn't involve the final velocity. And it's already set up for delta y, so we just got to plug in our variables. So delta y is equal to, we have 30 meters per second times 2 seconds plus 1/2 times, don't forget that's a negative 10 here, meters per second squared times 2 seconds, and then that's squared. So 30 times 2, we have 60 meters. 2 squared is 4, and then half of 10 is 5, so we got minus 20 meters. So your height there after 2 seconds is equal to 40 meters. Lastly, for part C, we want to know how far does the projectile land. So now we're solving for our delta x. So we'll put C here. Again, let's make that table. We have x and we have y. Now we're solving for that delta x, so we'll go ahead and put that in. Your delta y, so we're looking for how far this projectile it lands. So that means that it's going to be equal to 0 for your delta y. You're back at your initial launch height. We know v naught in the x direction is equal to 40 meters per second. V naught y is equal to 30 meters per second. Acceleration is equal to 0 over here. And over here, acceleration is equal to negative 10. Now we have a couple of different ways that we could solve this problem, and I'll go ahead and show you both. So what we could do is solve for our time like we did back in those horizontal projectiles, and then use that time on the x side, and then solve for our delta x. So let's go ahead and do that. So If we approach it that way, we're going to solve for time. So we're not worried about our final velocity here. So delta y would equal v naught t plus 1/2 at squared. Your delta y was equal to 0, v naught t plus 1/2 at squared. And so now all of my terms here have a t, so I could cancel one out. So 0 equals v naught plus 1/2 at. And so now we can rearrange this for t. So I have negative v naught, subtract that over, equals 1/2 at. Multiply both sides by 2, and then we'll divide by a on both sides. So the time would then equal negative 2 v naught all over a. Now we can substitute in our numbers. So negative 2 times 30 divided by negative 10. And that would be 6 seconds. Now there's another way that we could have solved for this here. And looking at this, we have, let's kind of make another table here for the y direction. We have acceleration is equal to negative 10 meters per second squared. We have v naught is equal to 30 meters per second. What we could say is that our final velocity is now equal to negative 30 meters per second. And then we're going to solve for time. Now let's go back and look at that. In our projectile, over here when we drew our velocity vectors, remember we said that our initial vertical velocity is equal to the negative final velocity, this right here. So that's where that would come from. So you could do that, and then we would use a different kinematic equation here. And so what we would have is v is equal to v naught plus at. And then we would solve for our time. So that would give me v minus v naught divided by a is equal to t. And so your final velocity was at negative 30 minus 30 divided by negative 10, and that's equal to your t, and you would still get t is equal to 6 seconds. So either way you approach that problem when you built your table, you would still get the same time there of 6 seconds. Now the last step is to solve for that delta x. So now we have time, let's fill it in here, is equal to 6 seconds. Now we have three things on the x side, so we can go ahead and use our kinematic equation to solve for our delta x. So I'm not worried about the final velocity here. So I have delta x is equal to v naught t plus 1/2 at squared. And we have a 0, so our acceleration, so all that is gone. So my delta x is just equal to v naught, which is 40 meters per second, and my time was 6 seconds. So your delta x here is equal to 240 meters. So again, there's a lot of similarities between the horizontal projectiles and those launched at an angle. The main difference is that now we have an initial vertical velocity, whereas before we didn't. Okay, so this is the big difference here. As far as solving the problems, we'll solve them kind of similarly to our horizontal projectiles. Make your table with your x and y components, fill in your knowns, Now you have the two knowns, right? Your acceleration in the x direction is 0. Your acceleration in the y direction is equal to -10. And then fill in the information from our problem, resolve your initial velocity to the x and y components, and then you can start solving from there.